Oh, I was very stupid throwing out the...
No, this is right. Just
yeah, because it's completely confused.
No, okay.
Oh my God, everything is gone almost. It was near a heat source. 34 degrees in Belgium when I did this. This is a picture of spaced time. Let me just explain where we will make a dynamical version, right? So I have drawn, this is really bad, but you see here these vertical planes, they represent the non-commutative world topology. The commutative shadow of every such plane is the line here. You should think that the line, all the lines are fuzzy now, the line is part of the picture, but I draw it here, is the commutative shadow. So you can think this is space-time, if you want, for physicists. It can be always the same space-time for physicists, but it can also be a different space-time. And if it's the same space-time, there may be automorphisms between the space at every moment of the evolution. This big T, for me, of course I'm going to say is a kind of time, but since if I say this space-time, then time is somewhere here. But there's an irreversible time that I use to make the dynamic process. So this T is for me just a totally ordered set. It can be a group, it can be of dimension 7, if you want, and this 4, this 7, and this, but you don't see it, 11 or so. But for me, there are many possibilities. The universe is only one example, and I don't know exactly how to fit it in.
What did you call the horizontal time? The big T?
This I call an irreversible. It's only a totally ordered set for the moment, and I call it an irreversible time if you want a name. And there's the relativistic time is in the commutative shadow, and I did not put in the model any relation between this irreversible time and the relativistic time. But I was tempted to assume at every moment a map from this big T to the time. That's what you should do. But I didn't do it.
Is there any significance of the two gaps that you've got in the shadows? Is that a delta time? Is that a small time between those two?
Yeah, every time there is a thing. There is a certain interval that's going to appear in a moment, and you can think it's the time scale. But there is a certain, especially, well, let me explain. So I have this non-commutative space moving by morphisms between them, structural morphisms that are given as evolution. It's the evolution of the universe as far as I'm concerned. We will never know these maps. In mathematics I can construct some examples, but the physical thing, this is God-given if you want. It is how the universe describes the geometry at every moment and how the geometry at every moment combines to the universe. So these are maps from one moment to another, linking. The geometries are different. The non-commutative geometries are different, and they don't have the same points. Why did I come to this idea? Because I don't have enough points to describe my topology on the non-commutative space. So I want to get these points from somewhere else. I want to import them from the past and from the future. And because observation is a dynamical thing, you need an observation. Suppose you want to describe the geometry at a certain moment by observation. Mathematically you don't do that, but physically you do. Then you need time. And what you get is dynamical information over a certain interval perhaps. And yet you act as if you know that on that moment. And this is of course a mistake, but not a bad mistake. But so let me explain. So the non-commutative world is moving via some morphisms that I don't know. In mathematics, in examples I can construct them. And I can construct them so that I get points, enough points. Right? But for physics there's an axiom. If you have this whole system with this very big irreversible time and the non-commutative space, and then you have all these spacetimes, maybe the same, you can assume that there's... I want to think that perhaps there are automorphisms allowed. So that when you move in time, there is isomorphisms between spacetime for every moment. This is very interesting point.
I'm just wondering how close this is to the sort of intuition that I had in my tool.
Yeah, well, let's go on, but everything is already here.
Right.
If I wait 5 minutes more, I think it's going to evaporate completely. My space-time is up in air. So, I don't have enough points, but there is an axiom that there are enough points when, if you want to be religious, God created the universe with enough points. But they're not all at the same time. right? So we have to allow some distance to find the point, so I define a temporal point. A temporal point is a thing in the topology. Oh god, everything is gone. Let's see, this thing here is an open in that topology. I'm mainly talking about the topology for now. And it was a point yesterday, or it will be a point tomorrow. So you, in these structural maps that connect the non-commutative spaces at times t, something is a point, but today and maybe not tomorrow. Of course, infinitesimally speaking. So I want to say that a temporal point is something that was a point or will be a point. And then, if there is enough points, that means that, well, the temporal points define the topology. So I cannot write every open as a union of points, or describe it, not as a union, but by a set of points. The magic word is set. The opens in this non-commutative world are not sets, they are opens, right? And if you go back to set theory, then your forced Boolean logic and all kinds of rubbish comes into it. So let's not do that a priori. So we don't do that. So we have, of course there is a difference. There are past points and future points in the temporal points. Now a point is always idempotent for the intersection. So I'm running a little bit forward, but in this non-commutative topology, the intersection is not commutative, yes, but the essential point is that not everything is idempotent for the intersection. This part from the Boolean logic, but it's much different from the quantum logic. It's more non-commutative than quantum logic. So intersection is not necessarily intersection A is not necessarily A. First I was embarrassed, later I was really euphoric for 3 days because I thought I had changed the world, but of course that was not true. At least my eyes saw some difference in the world that I didn't see before. And even that was not true. But okay. So, in a sense, this means that at every moment I have enough temporal points. Every open is a union of temporal points. And now, this doesn't relate to set theory immediately, because a point, a real point, is always an idempotent for the intersection. An idempotent for the intersection appears in the commutative shadow, that's spacetime. So you must think that the idempotents, just like in the Neumann regular ring, the idempotents are the Boolean thing. So the idempotents of my non-commutative world are the commutative world that you're calculating, but that you're thinking. So this is the space-time. So points that come from the past, because these maps are structural, they respect the structure of the thing that I'm talking about. They are idempotents. So points that are, the temporal points that are past points, they appear in the commutative shadow. All the uncertainty of the uncertainty principle comes from the future points. The future points are the ones that are not yet points, that have not been observed. So, that's it. That's in the model, in fact, and I think that's intuitively very clear. It's the future that is the problem, not the past, unless you do history. Then, here is now a thing. How, this is a very rough model, how are these things continuity and so on. So I have to put some very narrow, very simple axioms. And everything I put on will be much more easy than continuity. I don't have continuity in this framework, but I have sort of continuity in the sense that I have intervals in this irreversible time, and I have to...
But your cap T is continuous.
This T? Well, this is just a totally ordered set.
Oh, okay.
If you want a totally ordered group, or for evaluation or something, fine. If you want the real numbers, fine. But it's a totally ordered set, abstractly. I don't want to, so that's why I call it a takeaway lecture. I take away everything you want to use, so then I feel safe and I can say what I want. So, but no, I want minimal conditions. I really wanted to restrict to the absolute minimum to go where I want to go, and then I wanted to see what remains. And this is what remains. And it's related to string theory, you will see. I think, whatever. So, these temporal points, if you... What is the smallest object you want to observe as a physicist? Perhaps. So this is in the geometry, this is not particles. I sort of make a geometry that fits particles, I suppose, but it's geometric, it's mathematical, axiomatic, as there's no particles here, points. So the smallest thing you could observe is something moving, a point, say, moving in this non-commutative world, being dynamic and doing things, interacting with whatever there is. But that's sort of the